Hello, and I am Ugo, once again doing another problem. This one is the GCD. Sorry, it's taking a little time to get used to calling it that. I grew up being told it was called greatest common factor. Uh, so I'm used to GCF, not GCD. But that's fine. Same thing. Basically, what we're doing is we are given two integer numbers that are non-negative, thankfully. I mean, it wouldn't be difficult to handle it if it was negative. You just had to find the absolute value, I guess. Right? I think so. Uh, well, at least in my original solution, that's all you would have to do. I saw one of the discussion posts by Fu Kwa. I don't know how to pronounce the last name. I feel bad about that. But uh, yeah, he mentioned the Euclidean algorithm. I haven't heard of it before, or I hadn't heard about it before. So my original approach was considered naive, but I also try to optimize it as much as possible. The original solution was basically you find the smallest number. I don't think I have it here, do I? No, I forgot to submit it. I was originally doing it in C++, not realizing that we were supposed to be doing it in Python. But basically what you would do is you would first check, make sure that the numbers are not zero. If there is a zero, then just handle it properly. You know, if one of them is zero, just the other one is the number, because zero, the greatest common factor of a number with zero is in the number. And if it's 0, 0, then it's just 0. But yeah, so you check that, and then since it's non-negative, we don't have to worry about the absolute values. We just find whichever one is the smallest one. From there, we iterate backwards, and because we're iterating backwards, we're only going to be finding or looking for the first occurrence of a divisible number for both of them. So basically, we're going to be stepping backwards with I from the smallest number. The largest possible divisible number for both of them would be the smallest of the two, because then if it perfectly fits into both of them, it'll be like 5 divided by 5. You can't do 6 divided by 5, or I mean 5 divided or 6 or 5 divided by 6. So you can't have a number greater than the smallest one to do that for the greatest common divisor or whatever. That was my original solution. It was O of n, but it would be very bad in cases where you would have a very low greatest common factor. So an example would be like 1,999,999. In that case, then yes, it would be very bad. It also was the most efficient when you had perfectly divisible numbers, so like 5 and 10, it would be O of 1. This one is a little slower in terms of that in that case, but it's fine. It's consistently O of log n, because it basically cuts down numbers really quickly, and I'll get into that in a second. But yeah, that's the problem we're given. And this is the code I came up with after a second solution. So first, after finding out that this was even a thing, I looked it up because I was curious about it. I was like, okay, what is this thing? Because Fu seems to always have the craziest algorithms, and learning them would be helpful for me. I mean, if I just stick with the brute force or naive approach, then forever, then I'm not going to be valuable. So, yeah, it was an efficient method for computing the greatest common divisor between two integers. So when I saw this, I was like, okay, I have to understand it now. It's the thing we're looking for, right? So I looked at this video first. I watched it. I understood it, kinda. I didn't really understand why it worked or how we were guaranteed that it worked, but I saw what the repetition pattern was. So we would basically rewrite the division part into a sum and product of two numbers. So we would have 54 times a certain number, which would be the quotient, plus the remainder, because that's just a division, simple division. You have a quotient, and then you'd have a remainder, and then the remainder plus the product of the number that you're of the divisor and the quotient would give you the dividend. I think I used the terms correctly. I hope I did. But yeah, so the thing that was important though is we don't have to keep track of this, nor do we really have to keep track of this. We kind of do, but not really. Essentially, all we have to keep track of is the was it divisor? Oh, damn, I'm blanking right now. Sorry. We have to keep track of the remainder. That's the important thing, basically. And then, the previous remainder, right? So we assume that what's it called? That A is the previous remainder, or M, depending on which one you're looking at. Right here it's MN, and then right here it's AB. So basically what we're going to do is we're keeping track of the previous remainder and the next remainder, or the current remainder. And because of this type of like repeatedness, where we have to pay attention to the previous remainder and then the current one, and we're using that to solve the same problem, just putting them in different places, I initially thought of the recursive solution for this, which would just be using A. We keep track of A, and then we'll use the modulus of B and A. Oh wait, no, we would have to pass in B into the function again as A. So then it goes over here, and that's going to be the new A. And then, or the new B. I'm sorry. I'm messing this up. I should probably just look at this instead. So yeah, they're basically passing in the previous remainder as the new A, and then we'll be passing in the remainder of A divided by B as the new B. And if we keep repeating that, we'll basically get down to the point where we'll eventually get a remainder of 0, and when we get a remainder of 0, the answer is the previous remainder. So this case, he points up to the previous one, but we don't have to do that because we have it in the current function. It's just going to be in this spot instead of this spot. So knowing that, I created the recursive solution for it. That was my initial solution. Pretty simple. If the remainder that we currently have is 0, then we return A because that is the new one, because previous remainder is the answer. And once we get to 0 as a remainder, or the current remainder, and then we just keep calling the function, passing in the new remainder and the previous remainder as it. So I did that, and then I realized that this would actually be pretty simple to code an iterative solution for. And I was like, what is wrong with me? Why wasn't I thinking of that originally? I should have just seen those 2 lines of code and thought, okay, I could do this iteratively. But yeah, after a second or two, I came back to the problem. Sorry, I got a little distracted. But basically, I just rewrote it into a iterative solution doing the same thing, where while B is not equal to 0, so as long as as long as there is a remainder, we'll keep doing this process where we swap, where we will basically assign A to be the current remainder, or the previous remainder, and then make a new remainder based on A divided by B, and the remainder of that process will be the new B. And we just keep doing that, and then the answer will just be the A, or the previous remainder. So that was cool, but I didn't fully understand why this was kind of guaranteed to work. So I went to watch another video after that where I was like, okay, why does this work? And I just watched this whole thing, and it was like, okay, that's cool. So I think this visualization was cool because it was like, it kind of explained like what it kind of happening, where the greatest common divisor is basically going to be guaranteed to be like left alone as we slowly eliminate every reoccurrence of A in B So we have this large grouping, and we're just going to remove any occurrence of this number in here. So in this case, it would be remove all the occurrences of 54 that occur in 888. All 16 of them would get removed, and we could basically minimize the number that we have left over. And we're doing an interchanging operation where we're basically swapping the B to BA. So because of that, in this visualization, after we do that, we kind of look at this one and then we remove from here. So we have this little grouping, and we're just going to look for this occurrence over here, which is basically what's happening here. So, yeah, pretty cool. We have 24, that's the previous remainder, and we're looking for all occurrences of it within this number. And it occurs twice, so we basically remove that, and we pass this in as the previous remainder. And, oh no, this is the previous remainder. And now we're looking for all occurrences of 6 and 24, and we're removing that until we get 0. And once we get 0, essentially we are left with only one number, and that will be well, in this case, 6. I know in the visualization they leave it alone like that. I don't know if they do it later on. I remember they did it. Basically, if you repeat the process by one more step, this would be the new highlighted one, and you'd remove all occurrences of this here, and that would get you to 0. Once you have 0, you could basically assume that this is the greatest common divisor. So that's the actual logic and proof for why it would work. It kind of just eliminates all of the remainders occurrences in the yeah, it removes all previous remainders occurrences in the current remainder, or I guess current remainder, right? Yeah, current remainder. Wait, would it be current remainder? Sorry, it's a little weird, but it kind of makes sense, and it's pretty cool. I liked it a lot. And yeah, that's the solution for greatest common divisor. I know it says it took me 38 minutes. It didn't. I just left it open, got distracted, went somewhere else for a second. What did I write here? Oh, right. And on here, I didn't realize we were using class, so I didn't write self right here. But yeah, that's the greatest common divisor. Oh, right. The reason I switched from recursive to iterative was because recursive would be O of log n space along with O of log n time, which isn't the worst, but you know, the space is unnecessary if it's such a simple iterative solution to make. So rather than having O of log n space, I was like, okay, I can just change it to iterative, and iterative would be O of 1 or constant space, and where the only thing we're really making is temp to swap it. I didn't want to do the A B equal B A mod B. I could have done that, but I think that's less efficient because you're creating a tuple and you're basically just swapping the values of the tuple into a new tuple. So Python things. But yeah, I wanted to get as close as I could to the most efficient solution that I could think of. I mean, I think probably could have just done not here, and that probably would have been faster. I mean, I guess I could just do that right now. While it's while B, I guess, right? And then just submit it. Oh, it's slower. Whatever. Whichever. I mean, it's probably not slower. It's probably the same thing, but yeah. That's the difference between it. In this solution, it'd just be a quick little thing. Let's do the problem that was shown up there, which would be 54 and then 888. As you can see, it's 24 steps, nice and simple. We just keep going. It's iterative, no call stack usage. If I do this one, copy paste this one over here, And then we remove the self part here and then just change this to A and B. Then we go right here, 54, 888. Damn, it's one less step. Okay, I guess it's one less step, but I mean, the call stack is kind of long. So, like, all of this for what was essentially just a few steps. If we have a very large function or like large one, I feel like that could be an issue. So, that's the only reason I really changed it. It's not really that much of a big difference though. But yeah, it's of log n because of the division part. Pretty cool overall. I thought that was cool. Maybe I could do a better job of explaining why it's guaranteed, but I think this is fine.